Let's do a few more examples of integration by parts. We're asked to find the integral of t times e to the t with respect to t. Again, with integration by parts, it's all about identifying a u and a dv. The u should be something that's easy to take the derivative of, and often that's just going to be just a power rule problem. So if I let my u equal the t, it's really easy to take the derivative. Derivative of t with respect to t is 1. So 1 dt, or we could just say, in fact, we'll just call that dt, make it easy. Okay? I'll do that in blue. I've been doing those in blue, haven't I? Oops. So du is just a dt. All right, the other thing I need to identify in my problem is a dv. And the dv should be something that doesn't get worse when you integrate it, and you should know how to integrate it, of course. And e to the t is awesome because it's its own derivative and its own integral. So my v, which again, to be consistent, I'll put in blue for this video, is just e to the t again. So it may not look like we've gotten anywhere, but we actually have, because now I can rewrite this as my uv minus the integral of v du which, for this problem, my u is a t, my v is e to the t minus integral, my v is e to the t, my du is just dt. So there is my first step to this problem. Now, integration by parts, unfortunately, always has a couple parts to it, actually. You've got to do the integration by parts. Then you've got to look at the new solution, and it will involve an integral, this time of just e to the t. But hopefully that should be an easier integral, or at least it should look like you've made some progress. And in fact, we have, because as we just saw, e to the t is its own antiderivative. And now that we're done taking the antiderivatives, we'll add a plus c. And you can check my work for me if you'd like. If you take the derivative of t e to the t minus e to the t, you will end up with just plain old t e to the t, what we started with over here on the left. So there's my final answer for this problem. Let's do another example. Suppose we're supposed to find 3x squared sine hyperbolic x dx. Now, with this problem, what we'll have to be mindful of is the fact that just because you've done integration by parts once doesn't mean that's going to be enough. This is a perfect example. So let's take a look. I'm going to identify two things, and the problem is set up very nicely for me where I've got a 3x squared, which I can take the derivative of. That's my u. And the derivative will be 6x dx. Now notice that I could also take the integral of 3x squared, but I chose not to do that because if I took its integral, I'd get x cubed, and that actually is more complicated. And whenever you're doing integration by parts, the key is to make sure it gets simpler with each round. So that means my leftovers, dv, should be hyperbolic sine dx. And nice thing about hyperbolic functions is that you don't have to worry about negatives. Sine becomes cosine, cosine becomes sine, and that will be great. So now let's put it all together. So the formula is u times v, so 3x squared times v is cosine hyperbolic x minus v du. So that's going to be cosine hyperbolic x times 6x dx. Scoot over just a little bit so we can see that. All right, I could definitely clean that up a little bit more, couldn't I? So let's take this down here and clean it up. That's 3x squared cosine hyperbolic x minus, and I'll rewrite this. I like to put my variables out front. I've got a 6x, variables by themselves out front, and then I've still got the hyperbolic cosine of x dx. And now, this is where I've gotten to the part of the problem where I have no clue how to integrate 6x hyperbolic cosine of x. Well, that means it's time for another integration by parts. And unfortunately, that's just how it works sometimes. So I'll need to go to this integral and think that, well, I can't integrate this directly, but I can see that if I let my u equal, and this is a different u from before, so ignore all the stuff up here now. Just pretend that's not there. If I take that as my u, then my dv would have to be hyperbolic cosine of x dx. And what does that give me? Well, the u would become du, 6x becomes just plain old 6 dx. And then, again, hyperbolic sine and cosine, don't have to juggle any negatives, which is nice. There's my v. And I need to be very careful here because I have that negative. This negative out here means I need to be very careful when I plug into the formula. X squared cosine hyperbolic cosine of x minus, scoot over a little bit, and now let's plug in to the formula, u times v minus the integral of v times du. So that's sine hyperbolic times du is 6 dx. Now, a recommendation is when you're doing a second level of integration by parts, immediately distribute that negative so you don't forget. So I made the negative a positive, and then I negated everything on the inside. And good news is that now this 6 is a constant multiple. And I know what the integral of hyperbolic sine is, so to wrap up this problem, I'll write it out. 3x squared hyperbolic cosine of x minus 6x hyperbolic sine of x plus the integral of hyperbolic sine. Well, I've got that 6 first of all. I'll bring down the 6, the constant multiple 6, and then sine becomes cosine. And finally, I'll add my plus c. And there is a final answer to this problem. And it would take a little bit of work. You'd have to do a couple you'd have to do a couple of product rules, but you could actually take the derivative of this, and it would end up being 3x squared hyperbolic sine of x from that guy right there. Let's do one more problem. And this problem and the one I'm about to do were good examples of worst case scenarios involving integration by parts. In that last problem that I did, we had to do integration by parts twice. In this problem, we're going to have to do it twice, and there's going to be a trick to it, what I call integration by parts with cycling. So we'll see what I mean by that in this example. where we're going to find the integral of e to the w sine of 2w dw. So this looks like the perfect setup for an integration by parts problem, and the reason why it looks great is because we've got two things multiplied together. We've got e to the w and sine of 2w multiplied together. Now, I need to pick my u first. And I should pick my u to be something that I can take the derivative of. And I'm going to actually pick my u to be sine of 2u. And the reason why I pick sine of 2w is because it's easier to take the derivative of sine of 2w than it is to take the antiderivative. You could do the antiderivative using substitution, but if you want to, you don't really want to mix a substitution problem into a parts problem. So I'll let that be my u, and that would mean that the rest of this will become my dv, e to the w dw. So that means my v would be e to the w just by itself. I'll take the derivative on the left to get sine becomes cosine of 2w. Now, chain rule says I've got to bring out the derivative of the inside, so that 2 pops out there on the left, and I've got to have a dw involved as well. So let's put this all together, remembering the formula, uv minus integral v du. That'll get me, my u is sine of 2w, v is e to the w, minus integral. My v is e to the w, my du is 2 cosine of 2w dw. So let's clean up a little bit here. Get rid of my formula that I sketched out really quickly down there. And I'll clean up this next line. So I've got sine of 2w. You could also reverse the order if you like, EW, minus, now I've got this 2 on the inside here. Sometimes I find it easier if I just bring it out here to the left. Actually, no, I'm sorry. Let's hold off on doing that. It's hard to tell, when you're doing these problems at first, whether it's best to keep it inside or bring it to the outside. But I'm going to hold off on that, actually, for this problem. So I'll just stick it out here in the front. 2. And again, I want my u to be something it's easy to take the derivative of. So my 2 cosine of 2w, I think that's what I'll choose to be my u for this time around. And then what's left? Well, I still have my e to the w and a dw. And that'll be my dv. So let's write this all out. My u is 2 cosine of 2w. My dv is e to the w dw. And let's see, my du, if I take the derivative, the 2 is going to pop out from the inside, multiply by 2 to get 4. Cosine will take the derivative, become negative sine, 2w. And going backwards the other way, e to the w integrates to just e to the w by itself. So now, we'll rewrite. We've got sine 2w e to the w minus, and we'll throw out some big parentheses for the integration by parts because of the minus that's out front here. U times v would be 2 cosine of 2w times v, which is e to the w, minus the integral. And now I've got v du. So I've got e to the w, and du is negative 4 sine of 2w dw. And I'm going to close that parentheses on the far outside here. So these two parentheses match. And that's all well and good. Let's make sure I've got lots of negatives going around here, right? So let's make sure I distribute that negative. All right. And let's clean up. And I'm going to give myself a little bit of room here for a reason that you'll see in a moment. So I've got sine 2w e to the w minus 2 cosine 2w e to the w. And then finally, now I'm going to bring this negative 4, you see right here, I'm going to bring that to the outside. Minus 4 integral e to the w sine of 2w. So this is awful. At least it seems awful, right? Because it looks like I'm right back where I started. I've got an e to the w sine of 2w. And that's what I was asked to integrate. E to the w sine of 2w. But let's go ahead and rewrite that here on the left. My problem, e to the w sine of 2w dw. And again, I've got it on both sides of the equation. Both integrals here are the exact same integral. That's actually great news. This is great news because the one final trick, we've cycled. And if you've cycled, what you hope is you've cycled with this coefficient. And it's that coefficient. If it's plus 1, you're out of luck. But if it's any other coefficient, like a minus 4, you can undo it by adding it to both sides. It's the same integral. I'm not going to bother writing it out on both sides. I'm just going to add 4 of that integral to both sides. And lo and behold, here's what I've got. I've got 5 of the integral I was asked to figure out its value of. And here they've all canceled, leaving me with just sine of 2w e to the w minus 2 cosine of 2w e to the w. And notice I don't have any more integrals on the right-hand side, so I have my plus c on the right-hand side to make up for that. The very final step, I'm not going to bother rewriting this entire line. I'm just going to take this 5, divide by it on the left, and divide by it on the right. So on the left, it has canceled completely, leaving me with my final answer, sine 2w e to the w minus 2 cosine 2w e to the w, all divided by 5 plus c. Now the final thing you might notice is that, well, shouldn't I have made this just a little bit longer? And technically, yes, I should have divided both sides by the 5. However, I did not. And here's the reason why I did not. The reason why I didn't is because that c is an arbitrary constant. So if you take a random constant and divide it by 5, you've just got yourself another random constant. So to make my problem just a little bit cleaner looking, I only put the fraction over the non-constant part of my antiderivative. And that is my final answer. Takes a little bit of work when you've got a couple of integration by parts involved, especially when you have to cycle there at the end, but it allows us to integrate a lot more functions than we were able to do with just substitution or more basic methods.